So now we look at prime numbers. What is a prime number? A natural number is a prime number if the only dividers are 1 and the number itself. So if you have a number n larger than 1, a natural number larger than 1, if it's only divisible by 1 and n, and of course it's divisible, all numbers are divisible by 1 and themselves. But if these are the only divisors of this number, then we call it a prime number. Otherwise it's called a composite number. That means, for example, that we have the prime numbers are 2, since 2 is only divisible by 1 and itself. And that's the only even prime number that exists. All the other prime numbers are odd. And 3, 5, 7, 11, 13, and so on. And the composite number are the remaining numbers. 4, larger than 1, 6, 8, 9, 10, 12, and so on. So we have, for example, all the prime numbers to the left here and all the composite numbers to the right. And we see that all composite numbers can be written in these rectangular arrays. But that's not possible with the prime numbers, so you can group them like this. We see here that we have written dots here, continuation dots, implying that there are infinitely many. There actually are infinitely many prime numbers, but that we will prove later on. Say that if you want to find out if you have a certain integer, let's say we want to find out if it's a prime number or not. For example, if we just take some random number here, then it should end with an odd number, because it ends with an even number. We see directly it's divisible by 2, so it can't be a prime number. But let's take some other random number, an odd number. Then, is this a prime number or not? Then how should we check that? Yeah, well, we could try all numbers between 1 and this number, test if it's divisible by 2, if it's divisible by 3, 4, and so on, up to 3, 1, 2, 1, 8, 1 less than this one. If there are no numbers that divides this, then we know this is a prime number. But that, of course, is very tedious and hard work. Later we will see that all integers can be written as a product of prime numbers. So all integers can be written as a unique product of prime numbers. And that means that if this is not a prime number, this should be written as a product of some prime numbers. And that means that we don't have to test all integers here. We only have to divide by all prime numbers smaller than the number. To see, for example, if divisible by 2, if it's divisible by 3, then the next number, prime number is 5. If it's divisible by 5, then 7, 11, 13, and so on. But still, there are many numbers to check. But you can also show that if you have the number n, you want to check if this is prime number or not. It actually holds just to check up to the square root of n. So you only have to check these prime numbers up to square root of n. And if you don't find any prime number that divides the number, then we know that it's a prime number. So you only have to check these. And in my book I show a proof of why you only have to check up to square root of n. Still, only checking all the prime numbers up to this, there's still a lot of numbers we have to check. But that's part of the problem with prime numbers. It's difficult here. You have to check a lot of numbers. So it means a lot of hard work. But that's the thing with prime numbers. So for example, bank security systems are based on that it's hard to find if it's a prime number or not, or find prime factorizations. So it is a lot of work to do to check it. There is no known formula to calculate explicitly all the prime numbers. However, there is a method to finding all of them, and that's called sieve of Eratosthenes. And the method works in the following way. Let's say if you want to find all the prime numbers from 2 to some number n, for example 2 to 1000 or 2 to 100, for example. Okay, then you write up first all the numbers, then so 2, 3, 4, 5, as far as you want to continue. So let's say I want to now check only up to 20, and of course that's not so far, but just for the purpose of illustration. Okay, so which one of these are prime numbers? Then the method is like this. You start with 2, you know that's a prime number. Then you first take all the multiples of 2 and cross them out. So 4, 6, 8, 10, 12, 14. Because none of those can be prime numbers, because they contain a factor of 2. They're divisible by 2. So they can't be prime numbers. Okay. After having done that, you take the next one that you haven't crossed out and did not have a circle. From the left, you go here from the left. If it not have a circle and not crossed out, you take the first one. Then take all multiples of 3. So 6, 9, and you cross them out. 12 has already been crossed out. 15, 18. And then you continue in this way. So the next one is 5. Then you take all multiples of 5. In this case, they've already been crossed out. But if we would have continued further, you could have find some that wouldn't be crossed out. So the next one is 7, 14, and 21, and so on. But we only continue to 20 now here. Next one is 11. Of course, now it's you're stopping early. Otherwise, you just have to continue here. So 13, 17, and 19. And now you see that all those with the circle, those are the prime numbers. So in this way you can find all the prime numbers up to a given number. You see it takes some time, but at least it gives you an explicit method to find them. And that's called this sieve of Eratosthenes.